The Gini coefficient is a measure of statistical dispersion intended to represent the income distribution of a nation's residents, and is the most commonly used measure of inequality. It was developed by the Italian statistician and sociologist Corrado Gini and published in his 1912 paper, Variability and Mutability. The Gini coefficient measures the inequality among values of a frequency distribution. A Gini coefficient of 0 expresses perfect equality, where all values are the same. A Gini coefficient of 1 expresses maximal inequality among values. However, a value greater than 1 may occur if some persons represent negative contribution to the total. For larger groups, values close to or above 1 are very unlikely in practice. The Gini coefficient was proposed by Gini as a measure of inequality of income or wealth for OECD countries in the late 2000s, considering the effect of taxes and transfer payments. The income Gini coefficient ranged between 0.24 to 0.49, with Slovenia the lowest and Chile the highest. African countries had the highest pre-tax Gini coefficients in 2008-2009, with South Africa the world's highest, variously estimated to be 0.63 to 0.7, although this figure drops to 0.52 after social assistance is taken into account, and drops again to 0.47 after taxation. The global income Gini coefficient in 2005 has been estimated to be between 0.61 and 0.68 by various sources. There are some issues in interpreting a Gini coefficient. The same value may result from many different distribution curves. The demographic structure should be taken into account. Countries with an aging population, or with a baby boom, experience an increasing pre-tax Gini coefficient even if real income distribution for working adults remains constant. Scholars have devised over a dozen variants of the Gini coefficient. Definition: the Gini coefficient is usually defined mathematically based on the Lorenz curve, which plots the proportion of the total income of the population that is cumulatively earned by the bottom X% of the population. The line at 45 degrees thus represents perfect equality of incomes. The Gini coefficient can then be thought of as the ratio of the area that lies between the line of equality and the Lorenz curve over the total area, under the line of equality, i.e., G equals A. If all people have non-negative income, the Gini coefficient can theoretically range from 0 to 1. It is sometimes expressed as a percentage ranging between 0 and 100. In practice, both extreme values are not quite reached. If negative values are possible, then the Gini coefficient could theoretically be more than 1. Normally the mean is assumed positive, which rules out a Gini coefficient less than 0. An alternative approach would be to consider the Gini coefficient as half of the relative mean absolute difference, which is a mathematical equivalence. The mean absolute difference is the average absolute difference of all pairs of items of the population, and the relative mean absolute difference is the mean absolute difference divided by the average, to normalize for scale calculation. Based on just two levels of income, the most equal society will be one in which every person receives the same income. The most unequal society will be one in which a single person receives 100% of the total income and the remaining people receive none. While the income distribution of any particular country need not follow simple functions, these functions give a qualitative understanding of the income distribution in a nation given the Gini coefficient. The effects of minimum income policy due to redistribution can be seen in the linear relationships. An informative simplified case just distinguishes two levels of income, low and high. If the high-income group is U% of the population and earns a fraction F% of all income, then the Gini coefficient is F-U. An actual more graded distribution with these same values U and F will always have a higher Gini coefficient than F-U. The proverbial case where the richest 20% have 80% of all income would lead to an income Gini coefficient of at least 60%. An often cited case that 1% of all the world's population owns 50% of all wealth, means a wealth Gini coefficient of at least 49%. Known distribution function given the normalization of both the cumulative population and the cumulative share of income used to calculate the Gini coefficient. The measure is not overly sensitive to the specifics of the income distribution, but rather only on how incomes vary relative to the other members of a population. The exception to this is in the redistribution of wealth resulting in a minimum income for all people. When the population is sorted, if their income distribution were to approximate a well-known function, then some representative values could be calculated. A continuous income distribution may be represented by a probability distribution f, where f dx is the fraction of the population with income between x and x plus dx. If f is the cumulative distribution function for f, then the Lorenz curve L may then be represented as a function parametric in L and f. For some income probability distributions, the Gini coefficient can be directly calculated. In the table below, some examples are shown. The Dirac delta function represents the case where everyone has the same wealth. General case: the Gini index is defined as a ratio of the areas on the Lorenz curve diagram. If the area between the line of perfect equality and the Lorenz curve is A, and the area under the Lorenz curve is B, then the Gini index G equals A. Since A plus B equals 0.5, the Gini index is G equals 2A, or G equals 1 to 2B. If the Lorenz curve is represented by the function y equals L, the value of B can be found with integration, and in some cases, this equation can be applied to calculate the Gini coefficient without direct reference to the Lorenz curve. For example, for a population uniform on the values y, I equals 1 to n, indexed in non-decreasing order, this may be simplified to: this formula actually applies to any real population, since each person can be assigned his or her own y. For a discrete probability distribution with probability mass function f, where y, I equals 1 to n, are the points with non-zero probabilities and which are indexed in increasing order, where n. This formula is also applicable in the limiters. For a continuous probability distribution with cumulative distribution function f that has a mean mu and is 0 for all negative values of y, the latter result comes from integration by parts. Since the Gini coefficient is half the relative mean absolute difference, it can also be calculated using formulas for the relative mean absolute difference. For a random sample S consisting of values y, I equals 1 to n, that are indexed in non-decreasing order, the statistic is a consistent estimator of the population Gini coefficient, but is not, in general, unbiased. Like G has a simpler form. There does not exist a sample statistic that is in general an unbiased estimator of the population Gini coefficient, like the relative mean absolute difference. For some functional forms, the Gini index can be calculated explicitly. For example, if y follows a log-normal distribution with the standard deviation of logs equal to, then where is the error function? Sometimes the entire Lorenz curve is not known, and only values at certain intervals are given. In that case, the Gini coefficient can be approximated by using various techniques for interpolating the missing values of the Lorenz curve. If for the known points on the Lorenz curve, with the xk indexed in increasing order, so that xk is the cumulated proportion of the population variable, for k equals 0, n, with x0 equals 0, xn equals 1. Yk is the cumulated proportion of the income variable, for k equals 0, n, with y0 equals 0, yn equals 1. Yk should be indexed in non-decreasing order. If the Lorenz curve is approximated on each interval as a line between consecutive points, then the area B can be approximated with trapezoids and is the resulting approximation for G. More accurate results can be obtained using other methods to approximate the area B, such as approximating the Lorenz curve with a quadratic function across pairs of intervals. or building an appropriately smooth approximation to the underlying distribution function that matches the known data. If the population mean and boundary values for each interval are also known, these can also often be used to improve the accuracy of the approximation. The Gini coefficient calculated from a sample is a statistic, and its standard error, or confidence intervals for the population Gini coefficient, should be reported. These can be calculated using bootstrap techniques, but those proposed have been mathematically complicated and computationally onerous even in an era of fast computers. Ogwang made the process more efficient by setting up a trick regression model, in which respective income variables in a sample are ranked, with the lowest income being allocated rank 1. The model then expresses the rank as the sum of a constant A and a normal error term whose variance is inversely proportional to yk. Ogwang showed that G can be expressed as a function of the weighted least squares estimate of the constant A, and that this can be used to speed up the calculation of the jackknife estimate for the standard error. This method only requires the use of ordinary least squares regression after ordering the sample data. The results compare favorably with the estimates from the jackknife, with agreement improving with increasing sample size. However, it has since been argued that this is dependent on the model's assumptions about the error distributions in the independence of error terms, and that these assumptions are often not valid for real datasets. It may therefore be better to stick with jackknife methods such as those proposed by Yitzhaki and Karagiannis and Kovacevic. The debate continues. Guillermo Jasso and Angus Deaton independently proposed the following formula for the Gini coefficient, whereas mean income of the population, pi, is the income rank P of person I, with income X, such that the richest person receives a rank of 1 and the poorest a rank of n. This effectively gives higher weight to poorer people in the income distribution, which allows the Gini to meet the transfer principle. Note that the Jasso-Deaton formula rescales the coefficient so that its value is 1 if all the are 0 except 1. Note however Allison's reply on the need to divide by n squared instead. Pfau explains another version of the formula. Generalized inequality indices. The Gini coefficient and other standard inequality indices reduce to a common form. Perfect equality. The absence of inequality exists when and only when the inequality ratio equals 1 for all j units in some population. Measures of inequality, then, are measures of the average deviations of the from 1. The greater the average deviation, the greater the inequality. Based on these observations, the inequality indices have this common form, where Pj weights the units by their population share, and F is a function of the deviation of each unit Rj from 1, the point of equality. The insight of this generalized inequality index is that inequality indices differ because they employ different functions of the distance of the inequality ratios from 1. Gini coefficients of income distributions. Gini coefficients of income are calculated on market income as well as disposable income basis. The Gini coefficient on market income, sometimes referred to as pre-tax Gini index, is calculated on income before taxes and transfers, and it measures inequality in income without considering the effect of taxes and social spending already in place in a country. The Gini coefficient on disposable income, sometimes referred to as after-tax Gini index, is calculated on income after taxes and transfers, and it measures inequality in income after considering the effect of taxes and social spending already in place in a country. The difference in Gini indices between OECD countries, on after-taxes and transfers basis, is significantly narrower. For OECD countries, over 2008-2009 period, Gini coefficient on pre-taxes and transfers basis for total population ranged between 0.34 to 0.53, with South Korea the lowest and Italy the highest. For United States, the country with the largest population in OECD countries, the pre-tax Gini index was 0.49, and after-tax Gini index was 0.38. In 2008-2009, the OECD averages for total population in OECD countries was 0.46 for pre-tax income Gini index and 0.31 for after-tax income Gini index. Taxes and social spending that were in place in 2008-2009 period in OECD countries significantly lowered effective income inequality, and in general, European countries, especially Nordic and continental welfare states, achieve lower levels of income inequality than other countries. Using the Gini can help quantify differences in welfare and compensation policies and philosophies. However, it should be borne in mind that the Gini coefficient can be misleading when used to make political comparisons between large and small countries or those with different immigration policies. The Gini index for the entire world has been estimated by various parties to be between 0.61 and 0.68. The graph shows the values expressed as a percentage in their historical development for a number of countries. Regional income Gini indices according to UNICEF, Latin America and the Caribbean region had the highest net income Gini index in the world at 48.3, on unweighted average basis in 2008. The remaining regional averages were Sub-Saharan Africa, Asia, Middle East and North Africa, Eastern Europe and Central Asia, and high-income countries. Using the same method, the United States is claimed to have a Gini index of 36, while South Africa had the highest income Gini index score of 67.8. World Income Gini Index since 1800s. The table below presents the estimated World Income Gini Index over the last 200 years, as calculated by Milanovic. Taking income distribution of all human beings, the worldwide income inequality has been constantly increasing since the early 19th century. There was a steady increase in global income inequality Gini score from 1820 to 2002, with a significant increase between 1980 and 2002. This trend appears to have peaked and begun a reversal with rapid economic growth in emerging economies, particularly in the large populations of BRIC countries.